Thank you so much for the introduction. Thank you so much for hosting me, for organizing this session, Professor Witty-Young. I really appreciate your help with that. I'm also grateful for New Zealand Mathematics Society, who chipped in and made this visit possible. This is my first time to split my attention between the actual and the virtual audience that are in different geographical places for me. So I will try to split my attention in this way. I was thinking that this idea of talking about learning and teaching proof might be of interest for this community and also for me to learn from your experiences here, if this is something that is an issue, if this is something that is of interest, because it's an international long-standing theme of understanding how students come to understanding and comprehension of proof. And we especially see that in the transition to university, which is something that our mathematicians in Auckland are talking about in different ways. And it would be interesting to learn from your experiences as well. This is a collaborative work, the data for which were collected a few years ago by Nicole Liu, who was a master's student, and Sung Wong Kang, who was just finishing his high school degree and now is in UCL. So when we look at the literature that talks about students' learning of proof, some technical issues were supposed to happen at some point, so it's good when they happen early. Okay, so when we look at the literature that talks about the transition to proof, it is quite common in many countries that the learning of proof is postponed quite as much as possible, I would say. In the mathematics curriculum, in some places it is explored somehow in the context of geometry, maybe in middle school, high school. In other places it is skipped for various reasons, to the extent that some students can be exposed to the idea of proof only in the later years of university. So we're talking about like second year and beyond. And the way that some scholars and even teachers approach that throughout their mathematics education journey, students develop some mathematical toolbox, and it had a range of tools, and the only tool that was missing is the tool of proof. Okay, so we will add it at this point. Surprise, surprise, it is not as simple as this picture suggests, and the issue has been long-standing for decades. So this motivates many people to reconsider and conceptualize it from different perspectives. Almost 5 years ago, there was a huge compendium composed by international community, and the topic of proof was received dozens of pages there, reviewing all the literature that was current at that time. And the Stylianides brothers and Keith Weber, they distinguished between three main approaches to proof that the community takes and considers this issue. So one is cognitive, where proving is seen as generating a logical deduction that links premises with conclusions. Another one is constructivist, where proving is seen as an act of convincing, either yourself or maybe first yourself and then someone else. And they also talk about the social perspective, where proving is seen as an activity that is embedded in a community. And within this last social perspective, the emphasis is on the activity rather than on the understanding. And another distinctive point of this approach, that proving is seen as a comprehensive endeavor rather than a collection of smaller size tasks that students need to master. The emphasis is on the meaning that the community endows proofs with and the usage that actually students and teachers make of these proofs. And the cognitive and the constructivist perspective dominate the literature, especially the one coming from the US, but also the UK. When the social perspective, then 5 years ago, it was described as less developed, not coherent, lacking common, widely used concepts. Sorry, 7 years ago. I wouldn't say that much changed since then, because not many people jumped into this perspective. So this is what we were trying to do with this work. We were interested in considering how proof can be thought from the social perspective. We were using Thinking as Communicating, the communication framework by Anna Svart. Can you raise your hand and let me know if you ever heard about that or familiar with that to some extent? Okay, awesome, thank you. So this is a particular theoretical framework that looks at learning and teaching through the lens of communication. So this neologism is like an invented word that combines cognition and communication together. Professor Svard, whose work was influenced by the great social-cultural thinkers of our time, Lev Vygotsky, Jean Lane, Etienne Wenger, and Ludwig Wittgenstein. If I need to try to describe the commognitive framework in one slide, I was thinking about what kind of visual metaphor I can offer you for those who are less familiar with that. So I thought that maybe when we think about a typical theoretical framework, the underpinning assumption of how it works, it's usually something along these lines. There is some reality out there. People are thinking about this reality. Researchers are interested in how people are thinking, but it's impossible to get into people's head. So we need to compromise on the next second best, which is what they say. So many frameworks see a personal discourse as a window into one's individual thinking. So again, this is not something of interest. This is just a compromise that we need to make for empirical reasons. The commognitive frameworks looks at that slightly differently, or maybe not slightly differently. The same idea of reality, and people who think about this reality, but they think about this reality not in an independent way when anyone invents their own way to think about that, but all of us are operating within some historically established discourses. And what we do, we develop a personal version of that, which is not exactly fully ours, but it's also not foreign to what is happening in the broader society or the broader community, and there are many communities of this sort. And within this framework, thinking is relocated in the communication that people generate. So again, the main difference is that thinking is associated with communication not as a window towards something else, but as the thinking itself. So it's quite a radical framework, and we will talk about what can be done with it. The main theoretical construct is the one of discourses, which are defined as different types of communication, set apart by their objects, kinds of mediators used, the rules followed by participants, and that define different communities of communicating actors. So this is to say that there are many discourses out there, there are many communities out there. They can have discourses that work nicely together, and sometimes there could be tensions of various sorts. Mathematics is also defined as a discourse within this framework, something that has historic rules that were established and refined and changed and accepted in some form right now. Okay, operatively speaking, when people want to distinguish between discourses, they look at the keywords that are specific to the discourse and how these keywords are used, which could be quite unique to mathematics, like isomorphism, It's not easy to find the use of this word somewhere else, but there could be other terms that are borrowed from other discourses and they are used in a particular way, for example, like a fraction or like a function. It's not unique to mathematics, but it's used quite distinctively in mathematics. Visual mediators, tables, graphs, notations, symbols, anything along these lines. Generally endorsed narratives or some sort of mathematical truth that are specific to the discourse, and routines, which are pattern ways to communicate and do stuff within mathematics. For example, proving is a particular way of activity in mathematics. The way we prove in mathematics is not the way that we prove in social science, for example, right? Okay, so equipped with all these tools, we started conceptualizing, okay, so how can we think about the transition to proof in mathematics through when we want to use the discursive lens? And with Anna's help, we started distinguishing between three types of discourses. So something that we called D1, which is a mathematical discourse where we generate a narrative, a mathematical narrative about mathematical objects, some sort of mathematical truth. But we not only generate the narrative, we do it through some sort of conventional algorithms. And by using them, we ensure the validity of the narrative. Opposed to that, there is a proof-based version of this discourse, something that we call D2. These are the discourses where the generation of the narrative and its endorsement, the showing of its validity, are seen as two separate processes. Let me give you an example. Let's assume that we are asked to solve this quadratic. So we could apply the quadratic formula and we could get the roots. So we generated the roots. The fact that these are the roots is a narrative that we generated through a conventional algorithm. Why these roots are valid, why this solution is correct? To a considerable extent, the formula ensures that. So we did not just found the roots, we did not just create them out of the air, we also ensure that they are valid. So this is what we call something which is conducted within D1, where the generation and the endorsement go together to such an extent that we don't even feel that we not only find stuff, we also prove stuff. Or the question of proving does not emerge because there is no space for it. But we could solve it differently. We could say, hey, check it out. A half and a third solve this equation. We know that a quadratic can have up to 2 roots, and these are solutions of the equation. So we found them all. So this is an example of a solution within this D2, where we generated candidates for roots out of the thin air, but using some other mathematical truth, we show that we found all of them. So the generation and the endorsement, we explicitly attended to them as two distinct processes, if it makes sense. And you notice that this second solution, it is based on different rules that we implemented tacitly. So first of all, we started with a true statement, right? That these are roots. And then we said, hey, we know some sort of a broader truth, and this is an instance of this broader truth. So this is modus ponens in some sense. So this is what we call rules of proofs. These are interdiscursive principles that underpin, we are going to focus on written proofs, but this conceptualization is easily extendable to other types of proofs that we use to create proofs to endorse mathematical statements that are true or to reject the false one. These are the hidden stepping stones that we put together to create a proof. But for us to be able to talk about these hidden stepping stones, we make them, we reveal them, we expose them, right? And this is what we call D3. When we talk about the narratives of how the proof works, and we articulate, we specify, we explicate, we spell out what is the logic behind what we are doing. We're not just doing stuff, we're also explicit about what is done. Why something can be endorsed and why something should be rejected. So the objects of this discourse are not mathematical objects like a function or a fraction, but the object is the rule itself. I thought about an analogy right now. You can think about that as some sort of an etiquette. When we talk about an etiquette, we talk about the rules of the society. When we don't talk about etiquette, we just implement the rules, right? We rarely talk about it. So going back to our previous example, we see that here was one rule of proof that we started with a true statement. We just implemented that. Modus ponens was another rule that we use. So this is this type of the solution. And the second that we spell these rules out, we raise to this meta level, to these three. In commognitive terms, this proof-based version of D1, it subsumes D1, meaning that everything that was, or many things that were true in D1, they remain true in D2, but some processes that we do there, they act differently. This is the point of tension. The way that we prove, or the way that we show that something is mathematically valid without being explicit about that, would be different from the request, hey, how do you prove it? So because of these forms of tension, we might be able, or we might need to talk about the rules of proof explicitly. And this is the underpinning assumption of this work. May explicit discussion of rules of proof help students partake in the new discourse, in the discourse where proof plays a significant part. Meaning, would everyone's life maybe not become easier, but at least become more transparent if when we want students to immerse in proof, we will talk explicitly about why we need it, what rules are going to change, and what are the new rules that we need to implement from this point onwards. And symmetrically, we have enough research to show us quite enough evidence to say, hey, if teachers just talk about that, and even if they model that beautifully, in many cases, it's not enough. So we also want students to engage with these rules and not just to be passive listeners of that. So this is the conceptual assumption of this work. Our aim was to characterize rules of proof that students developed after having been explicitly introduced to them as part of their transition to proof-based mathematics. We wanted to see how students formulate, explain, justify, and implement the rules when making their first proving steps. It was a special semester or a special program that we have in Auckland for mathematically motivated and academically inclined students in their last year of New Zealand school. They're in year 13, 7 years old in most cases. There is almost no proof in New Zealand school mathematics. They really need to take a very special path to see that in school. And this was a developmental research or co-learning partnership with a mathematician with many years of experience teaching first-year mathematics courses and thinking quite deeply about the idea of proof teaching. The way that this course usually runs, the mathematician spends around 3 hours at the beginning of the course talking about different aspects of proof, introducing students to them. Then come some examples of something that is not working well with proof, and then there are examples of a good proof. This is something that usually was happening. So just to give you a few examples of what kind of rules we put forward in this activity. So examples are insufficient to prove a universal statement. If we want to show that something is working for all cases, it's not enough to show examples. So this is something that was shown and discussed explicitly. So here are a few quotes. And there was a long list of explicit rules that the mathematicians spelled out and led a discussion in the classroom. What we wanted to see with our research questions is, when asked to engage with these rules of proof on their own, how the students' version of them compare to what was discussed in classroom. And another question that we had is, how do students' rules compare when they need to articulate it, when they need to spell them out, and when they need to implement it? Do they just talk the talk, or do they also walk the walk in this? So what we did, we systematically compared rules of proof that students endorsed, spelled out, and enacted to what was going on in the classroom. We developed a special activity for that. It's something that is called a script writing task. Anyone familiar with that? So this is a special format of a task that was developed by Professor Rina Tsatskis and Simon Fraser University with Natalie Sinclair and Peter Lichedachel. It's a general format of a task where learners, students or teachers are provided with the beginning of a mathematical dialogue that revolves around some issue. The issue could be mathematical, the issue could be pedagogical, it could be ethical, it could be moral, it could be didactical. And then they're asked to develop a dialogue, a fictional dialogue, through imaginary characters, when the student is supposed to script the discussion around this issue and to lead it to some sort of a resolution, if it makes sense. So this is quite a particular version of this scripting task that was developed together with the mathematician. And what it practically asks the students to do is to reflect on some sort of a mistake that either they made or they saw someone making in the context of proof, and discuss what is so mistaken about it and what's the better way to go around that. There were quite interesting details that went into the design of this task. So for example, we wanted the student themselves, through their voice, to be the person who corrects the mistake rather than to staying in the shoes of someone who does the mistake. So this is some sort of a play on the typical roles that is possible to do when designing this sort of tasks. So what we did, in addition to this very special task that was integrated in students' homework assignment, there were quite regular activities where they were asked to prove mathematical statements. So this provided us with some sort of a baseline for comparison. 71 students submitted their homework assignment. In this instant, we found 58 of them usable for our purposes because the rest were talking about something else. A typical dialogue that they scripted consisted of an exchange between a friend character who made some sort of a mistake and a student character who corrected it. So this was the gist of our data. And we saw a lot of rule-related narratives, kind of the rules that students articulated when they explained what went wrong and how it was supposed to go differently. Okay, so just a few general observations before we delve into the details. When we looked at the typical proof requiring tasks in this homework assignment that the students did, prove that the sum of irrational numbers can be rational, prove that blah, 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 blah. What we saw is that in all these cases, 100% of the students, they implemented the rules without articulating them. And only when they actually got to the script writing task where they needed to generate the dialogue, this is where we saw conversations about the rules. So in some sense, I will repeat this point. This kind of provided us with more evidence that there is an added value to these script writing tasks if we want students to reflect on the rules and not just act on them. We found a range of gaps between what the teachers and the students were discussing, and also a range of gaps between what they said one needs to do and between what they actually did in their group. So let me start with connections between what was discussed in the class, mostly led by the teacher, and what students were discussing in their scripts. So first of all, there were many cases of similar rules, something that was said by the teacher and it was repeated in one way or another by the students, which is something that we expected, and it was not very surprising. Maybe I will just jump to the more interesting cases. Okay, there were cases where students elaborated on what was said in the classroom, and since we had the video recording, so it allowed us to go actually line by line and see, hey, was it actually said, or is it something, is it student's addition, is it kind of the added value in some sense? So for example, a teacher said, examples do not prove universal statements. When in the dialogue, the students through their imaginary characters, right? So they were saying something, you need to consider the full range of your X and Y values, not just the most obvious cases. So it sounds like a very similar idea, but it's way more detailed than it was presented in the classroom. Also, we see here a shift, and this is something that hit us only after we looked at the data, something that we did not think about when we were actually carrying out this research, is that the teacher was very good with generating rules about what students should not do in a proof. It was way more difficult to provide guidance about, okay, so what's the way forward? And this is quite interesting because the students, in many cases, they were the one to shift from something that we called a restricting formulation, right? Examples do not prove universal statement. Okay, so what does prove universal statement? So students, in many cases, through their elaborations, they started talking about that. In some cases, the students extended the rules that were discussed in the classroom by introducing additional aspects. For example, a teacher had these nicely put sentences. Proof steps should be explained, right? Like sounds like 100% in all the cases, right? To explain how much, what's an explanation, how much explaining one needs to do. And here is an extended version of that from a student. When you're trying to disprove a statement with a counterexample that requires a proof itself, it must be proved. So we see that as a way more detailed approach to this rule compared to what actually the teacher was saying. So the student recognizes here that, hey, if I am offering a counterexample, I cannot just throw it out there. I also need to show that this is a counterexample as it should be. We found two new rules, something that emerged from the students and was not discussed in the classroom. So one of them is the issue of circularity. Proving a claim using what is required to be proved is clearly invalid, which is something that we see quite often when students use what they're trying to prove as part of the proof itself. So students in their script, they were criticizing this sort of approach. You are not actually proving anything going in circles. And the second new rule was some sort of a criticism, actually, that we saw to this general or more general rule that was discussed in the classroom. So the teacher was promoting the idea that proof steps need to be explained. So here is an example of a dialogue that a student composed. Imaginary friend, I was just trying 1D, but to solve that, you need to know that integers are closed over multiplication. Me, right, the student character. You see, to prove that you would also have to explain what multiplication does and what the definition of an integer is, right? You cannot just use it, you need to explain what it is. Imaginary friend. Oh, I see. So we must take some logical claims for granted, else we would forever be asking questions. me. Exactly, this is overkill, and we best not think so deeply, we will run out of paper. So this is quite different, if not to say the opposite, almost, to what was promoted in the classroom, showing kind of, hey, you cannot explain forever, you cannot go back forever. You need to know what should be accepted as it is at some point. Then we also compared between the types of rules that the students articulated in their scripts and what they actually did when they were proving mathematical statements. And I want to focus on maybe the most surprising findings that we found. So one connection that we did not expect was something that we called a radical rule formulation, but conventional enactment. So we saw instances where student characters in their dialogues insisted that the rule of proof needs to be implemented exhaustively or in a very particular way. But when they proved mathematical claims, they did not do that. So for example, in the dialogue, a student is arguing, when you're trying to prove a statement by using a counterexample that requires a proof itself, it must be proved no matter how clear it is. Everything needs to be proved. But when doing the proof as part of the same assignment, just on a different page, so for instance, the student used the square root of 2 as an irrational number without proving that, and it was not proved in the classroom yet. So we see that the standard that is set is not met by the student. We also saw instances of overgeneralized rule formulation and still a conventional enactment. So for instance, instances where student characters didn't specify the scope of rule of proof, making it sound like it works all the time in all cases, but actually when they did the proof, they deviated from that. So for example, proving by using example is the wrong way to prove something. This is what they insist in a dialogue, but or just remember not to make any assumption next time, but they used counterexamples and proved by contradiction in other parts of the assignment. And as mentioned, we saw many instances when in the dialogue, the students were talking about something that is not supposed to happen in a proof, but knowing these restricting rules was not sufficient for doing the actual proving. So to prove mathematical claims, they needed to do something and not just to forbid doing something. Mm-hmm. So we also see that as something interesting there that they did not discuss by enacted, if it makes sense. So let me summarize and discuss this whole work. So we wanted to contribute with this idea of this D1, D2, and D3 to the existing approaches to teaching and learning proof as another way to promote this framework in this area with some interest in the potential for different usages. We also were quite excited about the possibility of combining script writing tasks and the framework. We were encouraged by the idea that through engaging students in this type of task, it actually makes them go to this level of D3, or at least many of them, and to talk about rules of proof in one way or another. And we see potential of script writing tasks to advance proof learning and its analysis. The teacher was initially quite concerned about how we're going to assess these dialogues, but we found a way out. You're welcome to ask me about that. We see that not as an alternative to what people are doing already, but maybe as a complementary tool that opens new venues for things that maybe we could do differently. The rules of proofs that we found, they are not new to the literature. This is not our claim. Our claim is that we were able to see that in the literature, scholars are talking about students' issues with these rules of proof through showing proofs where students fail to enact these rules. So the issues with these rules emerge through unsuccessful student attempts in most cases. We showed that students are capable of, or at least some students are capable of not only failing to follow these rules, they can also communicate about them on some meta level after a relatively short period of exposure and familiarity. So we talk about that as a change of status in the sense we saw major overlaps between students and teachers' rules of proof. So, when this paper was reviewed, so someone, one of the reviewers wrote, okay, so why are you so excited about? So they just repeated what was going on in the class. Mm-hmm. And indeed, it was absolutely possible because they had access to the recordings, they had access to the material. But in none of the scripts, we found an exact copy-paste of what was done in the classroom. So from the communicational point of view, there is a natural and authentic phase that it's supposed to happen, which is called the ritual phase, where people individualize a broader rule. So they create their own version of that. So, and there is a value in that. It is not seen as something that should be taken for granted. And also, we saw that the students were discussing these rules in the context of the assignment, which was quite different from what was going on in the classroom. So the shift of a mathematical context and the capability to match the right rule in their own words to an appropriate situation, we see a value in that. Overall, I hope that you saw some examples of something that we claim that in many cases, some students' formulations of these rules were fuller, crisper, and more precise compared to what they were taught. We also saw that restricting rules prevailed over the guiding ones in the student scripts. Maybe it is a side effect of the activity that we design. So we push them, we nudge them to talk about a mistake. So maybe it relates to the fact that they were more naturally inclined to talk about something that it's not supposed to happen. Maybe it also was something that they mimicked from the teacher, who also was way better in guiding students what not to do rather than providing something informative in the sense. We also saw that for many students, rule enactment was more conventional than rule endorsement. So it was easier for them to enact the rule than to talk about that. And this is something that now we can reflect on that. We didn't think about that when we were conducting this study. That to be able to operate on this D3 level, on this meta level that we wanted, we need to offer them the terminology. We need to offer them the vocabulary. We want them to talk about examples and counterexamples. We want to talk about inference. We want to talk about modus ponens. We want to talk about proving and disproving. This is a vocabulary that someone needs to offer to them. They cannot reinvent it on their own. So when the classroom instruction was not very suggestive in terms of this vocabulary, this could also explain why it was difficult for all the parties involved to talk on this meta level. It's not just a matter of a goodwill, it's also a matter of a discursive tools. But it's also possible that the capability to talk about restricting and guiding rules does not develop in parallel. So maybe something is just easier than the other. With Young kindly promised implications, right? So I think that this study is too exploratory at this point to offer any implication about what other people should do or not do in their classroom. My main point is to kind of expand our thinking about that and maybe to encourage people to reflect on the approaches to that. But overall, I cannot think about a counter argument for why wouldn't we explicitly discuss rules of proof in our classroom and also encourage students to talk about these rules explicitly. Thank you so much. I'm really looking forward to your feedback.
Thank you.